Hey everyone, this is Dr. Walker. This is video 578, Amperes Law. Amperes Law is used to calculate magnetic fields of current configurations having a high degree of symmetry. We've just learned how to find magnetic fields due to current distributions using the Biot-Savart law, but Amperes Law can be easier to use if we have a high degree of symmetry. So let's go ahead and figure out what Amperes Law tells us. So let's look at a straight wire, and we already know what is the magnetic field produced by a straight wire. We've already used the Biot-Savart law to know that the magnetic field due to a straight wire is mu naught I over 2 pi r. It depends on how far away that you are, so if it does make circles around the wire. We already know the direction of the magnetic field. The current is going upward. You put your thumb upward, your fingers curl in the direction of the magnetic field, which would be counterclockwise. So now let's imagine a closed path, and we're going to choose a circular closed path that's going to happen to align with the magnetic field. This closed path that we are choosing is an imaginary loop that we are choosing. And around this imaginary loop, we want to calculate the line integral of B dot ds. So B is the magnetic field at the location of this imaginary loop that we've picked, and ds is a little line segment that is part of this loop. So this loop, like I said, is an imaginary loop. We're going to call it an imaginary Amperian loop that we are choosing. What does the line integral look like? Well, because we chose a circle, B is constant everywhere along this path, so it comes out of the integral. So we have B times the integral of line integral of ds. And then if we integrate ds, that means we're integrating it over the closed path, which is going to be the circumference of the circle. So the line integral of ds is going to be 2 pi r. But we also said that b is mu naught I over 2 pi r. So we're saying that our circle here does have a radius r. So this is b, and then the integral is 2 pi r. So it turns out that the 2 pi r's cancel out. And we're left with this big result, which is Amperes law, which is that the line integral of b dot ds is equal to mu naught I. We need to discuss it a little bit further. So first of all, the line integral of b dot ds means the line integral around this imaginary Amperian loop that we're choosing. Now we're going to choose it to take advantage of the symmetry. In this case, if we choose an Amperian loop that is parallel to b at all points on the loop, then it helps us because the dot product vanishes and the line integral just became b times the circumference. It doesn't have to be a circle, so it doesn't have to be the circumference. It can be the perimeter if it's a rectangle loop. But if you take advantage of the symmetry, the direction of the magnetic field produced is in the same direction as the little ds elements that make up your loop, then the line integral will be very easy to calculate. The other thing is what this I is. This is often called I enclosed. And that might be clear. You might think, well, we have this loop here, so the I that is enclosed within the loop. But sometimes it becomes a little bit unclear, especially when we have different shapes of currents. So the way that I like to think of I enclosed is I like to draw an open surface. You choose a different color here. Think of it as a net. It's an open surface where the opening is that perimeter of that loop. And you want to think of I enclosed as I penetrating. So how much current is penetrating or going through that surface? Now, I chose a random shaped surface, but if you chose a flat surface like this, then the current that is penetrating that surface, that is I enclose or I penetrate. That's the easiest way to think about what this I is. Another thing that is important is the sign of the current. Is it going to be positive or negative? And the way that we do this is we're going to curl our fingers in the direction of the loop that we have taken. So in this case, we took a loop that was counterclockwise. So we're going to curl our fingers counterclockwise and look at which way our thumb is pointing. In this case, our thumb is pointing upward. If the current points in the same direction as our thumb, then that current that's penetrating is going to be positive. But if the current is in the opposite direction, it's going to be a negative current. So that's important to know about the directions. Now, another thing I want to mention is, does any of this sound familiar? We are finding an imaginary loop around our current distribution that takes advantage of symmetry so that a line integral simplifies, and this expression allows us to solve for b, right? If the line integral becomes, for example, b times 2 pi r, then we can very easily manipulate this equation to solve for b. Does this remind you of anything? Hopefully, it reminds you of Gauss's law. We haven't seen it in a while, but they even look very similar, right? Gauss's law, you had a surface integral of v dot dA was equal to the charge enclosed within that Gaussian surface. Remember, if we had some kind of charge distribution, such as a positive charge distribution, here we have a current. The first thing we had to know is, well, which way is the electric field going? The electric field points away from it, right? And we had to know here, well, which way is the magnetic field? Magnetic field makes loops. And then once we know which way the electric field is going, we picked some imaginary Gaussian surface that took advantage of the symmetry. In this case, we wanted the electric field to be perpendicular to the surface at all times, so that the dot product vanished, and we ended up with E times A, where A was a surface area of that Gaussian surface. And then using this equation, we were able to find the electric field due to various charge distributions. So hopefully making this, looking at this helps you understand Amperes law a little bit better. If we take advantage of the symmetry and choose our Amperian loop carefully, then the integral simplifies and we're able to solve for b, just like we were able to solve for e. Okay, so that said, let's look at an example. This example says, write the magnitudes of the integral of b dot ds for the closed paths a through d from greatest to least. So Amperes law tells us that this line integral is equal to mu naught times I that's penetrating that surface made by that loop. So let's just look at each loop at a time. For loop A, which is this outer loop here, we can imagine a surface, open surface, but we can just also make it flat. And we can see that we have 3 currents going through the surface. Since we're only looking for the magnitude of this integral here, we don't have to worry about the sign of the currents. So we can just add the ones going in the same direction, subtract the ones going in opposite directions. So we're going to have 5 plus 1, which is 6, minus 2, we're going to have 4 amps. Don't worry about direction. For the loop B, which is this diagonal loop here, we have 2 and 1 in opposite directions. We're going to subtract them to get 1 amp. For loop C, which is horizontal here, we have 5 and 1 in the same direction, which is 6 amps. For D, the vertical loop here, we have 5 and 2 in the opposite directions. We're going to subtract them to get 3 amps. So I just calculated the I that was penetrating that surface, because whichever one has that greater I is going to have the greater integral. So when we rank this, it's going to be C, A, D, and B. So in the next few videos, we will do more involved examples where we will learn how to use Amperes law even more.